Good morning to all. Today we are going to see Weidmann-Franz law. What is Weidmann-Franz law? It is the ratio between thermal conductivity kappa and electrical conductivity sigma, which is directly proportional to the absolute temperature of the metal. That is, K by sigma is equal to LT, where K is thermal conductivity, sigma is electrical conductivity, T is absolute temperature, and L is Lorentz number. That value is 2.44 into 10 to the power minus 8 watt per Kelvin squared. For that, we have to know what is electrical conductivity, what is thermal conductivity, what is the expression for both, and from that we can find what is Weidmann-Franz law. For that, we'll see what is electrical conductivity. Electrical conductivity is the amount of electrical charges conducted per unit area per unit time per unit applied electric field, that is sigma is equal to q divided by TAE, that is equal to J by E mole per meter, where sigma is electrical conductivity, q is amount of electric charge, T is applied time, A is area of cross section, E is applied electric field. Here J is current density. Now we'll see the expression for electrical conductivity. Consider a metal rod. In the absence of electric field, there is no movement of charges in a particular direction. That is, the electrons, that is especially free electrons, move in a random direction. When we apply electric field to the metal rod with an electric charge E, the electrons move in opposite direction to the applied field. Here, the electron experience a force, a electron, that is F is equal to small e into capital E. This force accelerates the electron with the acceleration A. So, we are applying Newton's second law of motion, that is F is equal to m into E. Here, equation 1 and 2 will see the left hand side is equal. In both equations, left hand side is force only. So, we can equate the equations 1 and 2. So, we are getting acceleration, that is small a is equal to E divided by m. It is found that accelerated electron should be accelerated continuously due to the applied electric field. So, the electrons acquire the drift velocity, that is Vd. If tau z is collision time, then acceleration is taken as A is equal to Vd by tau, where A is acceleration, Vd is drift velocity, tau is collision time. When we apply in this equation, Vd is equal to A into tau. Substitute the equation, we are getting Vd is equal to E tau divided by m into E. That is equation number 5. As we already know that current density J is equal to N into E Vd, where N is number of electrons, E is charge of electron, and Vd is drift velocity. By substituting the Vd value, that is equation number 5, in equation number 6, we can get the equation number 7, that is J by E is equal to N E square tau divided by m. That is equation number 7. When we apply Ohm's law in this equation, current density J is equal to sigma E, we can very easily find the electrical conductivity expression, that is sigma is equal to N E square tau divided by m. That is equation number 9 is the required equation of electrical conductivity. Now we'll move into thermal conductivity. For measuring thermal conductivity, we are supposed to know what is thermal conductivity. We'll see. Thermal conductivity is the amount of heat conducted per unit area, per unit time, per unit temperature gradient. It is almost the same of electrical conductivity. Thermal conductivity kappa K is equal to Q divided by A T dt by dx watt per mil Kelvin per meter, where K is thermal conductivity, Q is amount of heat conducted, A is area of cross section, T is unit time, and dt by dx is temperature gradient, that is change in temperature with respect to x value. Now we'll see the thermal conductivity measurement expression. For that, we are going to consider a metal bar with two planes A and B, which is separated by a distance C. Here T1 is hot end and T2 is cold end. Let n be the number of conduction electrons and v be the velocity of electrons, and kb is the Boltzmann constant. See this figure. A plane is taken as T1 temperature, that is hot end. B plane is taken as T2, that is cold end, which is separated with the distance c. From kinetic energy theory of gases, we know energy of an electron is equal to half mv squared, that is kinetic energy is half mv squared. For kinetic theory of gases, that half mv squared is taken as 3 kBt divided by 2. Here we are taking 3 kBt T1 divided by 2, that is hot end we are taking. For plane A we are taking this value. In the same way, for plane B, that is kinetic energy of an electron at B position of the figure, that is cold end is taken as 3 kb T2 divided by 2. That is equation number 1 explains the kinetic energy of an electron at plane A, and equation number 2 explains the kinetic energy of an electron at position B, that is cold end. So the net energy transferred from A to B is the equation number 1 minus 2, that is 3 kb T1 minus T2 divided by 2. Now we are moving into the equal probability of electrons to move in directions. The electrons can move in all directions, that is 6 directions. So each electron travels with the thermal velocity v, and n is the free electron density. Then average of 1 by 6 nv electron will travel in one direction. So the number of electrons crossing per unit area in unit time, that is at C position, middle point, is equal to 1 by 6 nV. So the energy carried by the electrons from A to B is equal to average energy transferred from A to B and number of electron crossing per unit area. The product of these two will give the energy carried by the electron from A to B. So Q is equal to 3 kb T1 minus T2 divided by 2 into half NV. Multiplying these values, we are getting the equation number 5. Now, as we know, the thermal conductivity expression states K is equal to Q divided by A into dt by dx. For that, we have found what is the value for Q. We supposed to substitute the values in the above equation. So we are getting the high heat transferred per unit area per unit time is equal to Q is equal to K into dt by dx. So Q is equal to K into T1 minus T2 divided by 2 lambda, where lambda is taken as unit length. So by substituting these values, we are getting thermal conductivity K is equal to half NV lambda into KB. So we'll take the values of electrical conductivity and thermal conductivity and substitute in the Weidmann-Franz law. So we can deduce the Weidmann-Franz law equation. Weidmann-Franz law is nothing but the ratio between thermal conductivity and electrical conductivity. We have found what is electrical conductivity and thermal conductivity of a metal with an expression. So substitute the expressions in the given law. We can get the Weidmann-Franz law. K is half NV lambda Kb. Sigma is Ne squared tau divided by m. Substitute and simplify that, we can get the Weidmann-Franz law, that is K by sigma T is equal to 3 by 2 KB squared by E squared. Here the constant terms are taken, that is KB squared by E squared is taken as Lorentz number. So Lorentz number is equal to 3 by 2 KB squared divided by E squared. From that we can conclude that K by sigma is equal to L into T. This is the required Weidmann-Franz law derivation. Here it is proved that the ratio of thermal conductivity to electrical conductivity of the metal is directly proportional to the absolute temperature of the metal. What is the success and failures of this Weidmann-Franz law? Success is, it is used to verify Ohm's law, electrical conductivity, thermal conductivity of metals, and optical properties of metal also can be find out by using this Weidmann-Franz law. What are the drawbacks? We could not find the Compton theory, photoelectric theory, paramagnetism and ferromagnetism. And light radiation could not be explained by this law. Okay, these are the limitations of this law. In this session, we have seen what is Weidmann-Franz law and what are the derivations of electrical conductivity, thermal conductivity, and the substitution of Weidmann-Franz law. That is, we have deduced an Weidmann-Franz law expression for a metal. Thank you.